In this session, I'd like to show you the temperature gradient in the stars. So there are three ways to transfer energy in the stars. First one is a conduction. So conduction is an efficient way to transfer the energies in the degenerate gas. So like a white dwarf. Because the electrons need to move in a long distance to find an empty space, and the electrons move to a region where the degeneracy condition is not satisfied. Conduction is not efficient to transfer energy in a standard stars, but conduction is a very important way to transfer energy in the degenerate gas. Second is a convection. When the water starts to boil, so you can find these kind of the convection cell, because the energy is transferred from the lower plate to the upper plate. Unit cell, we call this is a convection cell. You can find the convection cell when you observe the boiling waters in the pans. The matters have to move from the lower regions to upper regions. Direct movement of materials. Third case is radiations. So in this case, photons are responsible for transfer of energies. So in this lectures, we consider the two cases. The convections, temperature distributions follow the adiabatic. So we are going to explain adiabatic. So adiabatic means change of the internal energy plus work. 1 over rho is due to the input of the heat. So in the adiabatic, the right hand side is 0. So from these equations, in the case of the adiabatic, du plus p pressures, the change of the 1 over rho is going to be 0. So we are going to consider this situation. Internal energy expressed with a p and rho's. In the case of the non-relativistic gas, 3 over 2 p over rho. And the relativistic gas, U is expressed 3 p over rho's. So in general, we can express the internal energy is expressed phi p over rho. By changing the phi, you can express this could be the internal energy for the non-relativistic gas, internal energy for the relativistic gas or photons. Single equation to describe the internal energies of the both cases. du is gonna be phi dp over rho minus phi p over rho squared d rho. Then you can substitute these expressions into this one. du plus p d 1 over rho equal phi dp rho minus phi plus 1 p over rho squared d rho. So from these equations, dp over p equal 5 plus 1 over 5 d rho rho. So from these equations, you can integrate in the both sides. Log p equal 5 plus 1 over 5 log rho plus integration constant. So from these equations, p is proportionate rho to the power index 5 plus 1 over 5. So we name it this is gamma. So this is rho gamma. Okay, so we call this gamma adiabatic exponent. In the case of the non-relativistic gas, adiabatic exponent, you can calculate 5 plus 1 over 5. It becomes 5 over 3. In the case of the relativistic gas or radiations, gamma is 4 over 3. When you blow on your hand, you will find the temperature of your breath becomes lower than your body temperatures, because the pressures is located. This is the equations of state. So higher temperatures is a higher slope. In the low temperatures, lower slope, because T corresponds to the slope. In the adiabatic expansions, the gas is changing from the higher pressures to the lower pressures. Then originally the pressures and the densities of the gas is here. Pressure is dropped from the higher pressure to the lower pressures. Then actually the temperatures of the gas is changing from the higher temperatures to lower temperatures. During the adiabatic expansions, actually the slope of the adiabatic expansions is a higher slope. Then we could consider the transfer of energies by photons. In this case, the white light passes a slab. During the transfer of photons, some of the photons are absorbed in this slab. Density is given by the law. Temperature is T. The original is the heat flux of the H is coming from the left. And the sum of the energy is lost during the light is passing through the slab. So dH is the loss of the heat flux because of the light is interact with the matters inside of the slab. Absorbed radiations should be the proportional to the incident flux. If we have a larger heat flux, more energy should be absorbed by a slab. And also that if we have so many gas inside of the slab, the more heat is absorbed. And also the length of the slab becomes longer, the more heat is absorbed. So the absorbed radiation dH should be proportional to the incident flux H and the density rho and the dr is the length of the slab. As a proportional constant, we choose a kappa. Kappa we call the opacity coefficient. This is a proportional constant. Once you understand opacities, you can express this equation. dH equal minus kappa H rho dr. If you consider this is a differential equations, you can express minus rho kappa dr. If we consider this rho kappa is a constant, then it becomes log H equal minus rho kappa r plus integration constant. So H is expressed H sub 0 exponential minus rho kappa r. Initial heat flux is H sub 0. And during the passing through, this heat flux is decreasing, following the exponential functions. When the R becomes 1 over rho kappas, this part becomes 1. So original heat flux is decreased by amount of the factor of the 1 over E. This length is a typical length to decrease the original heat flux. We call that this is the mean free path of a photon. And then now we'd like to introduce a new quantity of the optical depth. Optical depth is defined d tau. Tau is optical depth. D tau equal using the opacities minus kappa rho dr. So this is a measure of the transparency of the medium to the radiations. Opaque medium is a large optical depth. If the kappa is really large ones, optical depth becomes larger. In the transparent mediums, opacity is smaller, so meaning of small optical depth. So once we understand optical depth, we can define the surface of our stars. This corresponds to our position, our eyes. R corresponds to R infinities. And then you can look at stars. Photon is produced inside of the stars. They frequently collide with electrons or ions. And it's quite difficult to escape from the inside of the stars. But when the photon is come to the reach near the surface, just only the single collision might happen. And then we can determine the surface of the stars is if we counted the number of the collisions of the photons with the materials, there was only the single collision is happening. Optical depth in the ones. Using this optical depth, we could determine the surface of the stars. We call the photospheres. We solved this equation to determine the radius of a stars. And to find out the kappas, opacities, actually we need to consider the interaction between the matter and the photons. Matter is composed of the electron and the ions. Electron scattering. Photon is scattered by the electron. And sometimes free absorption. Photon is absorbed by the electron. And the bound free absorption. In this case, the electron is bounded by the nucleus. In the bound absorption, energy state of the electron is changing from the lower energy state to the higher energy state by absorbing the photons. But as I explained, C and D, we assume the electron is bounded by the nucleus. But inside of the stars, actually the temperature is too high for the nucleus to have electrons. So we can consider the free electron and the free ions. So we need to consider A and B process, electron scattering and free absorption. So to consider this situation, we could make a laboratory experiment or quantum simulations. Interaction between the electron and the opacity given by this opacity is a function of the density and temperatures. So power index is given by the A and B. So I just show you the one example. Average opacity is a 1 square centimeter per grams, and the average density is given by the 1 gram per cubic centimeters. Using this equation, we could find the mean free path, 1 over density and opacity. So 1 over density is a 1 gram per cubic centimeter, and opacity is 1 square centimeter per grams. And the gram is going to be cancelled out. Centimeter square is cancelled. So it becomes 1 centimeter. Finally, we'd like to find out the temperature gradient inside of the stars. So absorption of the radiation is absorption of the photons. Photon has the momentum. And the momentum is from the equation of energy is equal to Pc. So momentum is expressed energy divided by the c is the speed of light. dH corresponds to the energy absorbed in the slab. So dH divided by c is the absorbed momentum that we could find. Rate of the increase in the momentum is equal to the net force. So this is the rate of the increase of the momentums is equal to the pressure gradient. So difference of the pressure. This is net force, pressure difference. So this right hand side can be expressed using the gradient minus round P radiations, round R. And then for the dH is expressed kappa H rho dr. I explained, we can substitute kappa rho dr. From this equation, we have get this expression. And for the P radiation, this radiation pressures of photons is 1 over 3 AT to the fourth. You can substitute. Then H is expressed this one. The H is a heat flux per unit areas. We consider the stars. Then you have to multiply. So in the case of the R, surface area of a sphere is expressed 4 pi R squares. You have to multiply the 4 pi R square times H to find the total flux of the F. So total flux of the F from the spheres with the radius of the R can be expressed in this equation. So from this equation, temperature gradient in the stars can be calculated. This equation. Flux is related to the temperature gradient. So this is the end of this session.